Hello everyone. In this today's lecture, we are basically going to deal with the Unit 2. And in the very first Unit 2, the first topic that we are going to deal with is the attenuations. I mean, in the first unit, we have discussed about what are the different types of optical fibers and what is the basic phenomena that is related to an optical fiber. In that, we have dealt what is the meaning of a total internal reflections, because of which light ray propagate through an optical fiber. Apart from that, we have also discussed what are the different types of categories in which your optical fiber have been divided based upon the index profiles as well as based upon the mode. So this was the discussion about what are different types of optical fibers. Apart from that, we have discussed about how a mode is formed. Then what is the various advantages, disadvantages of an optical fibers. Apart from that, we have discussed some more phenomena and ways like evanescent wave. Apart from that, we have also discussed Gauss-Hansen effect. So this was the overview about the unit first. So in the unit 2, we are basically going to deal what are the various effects that get associated with the optical fibers. Like if we have discussed about what are the basic phenomena related to optical fiber in unit 1. Now, once we got the basic idea about what is the basic phenomena through which a light propagates in an optical fibers, what is the different rays like skew rays and Meridional rays. After that, we should know what are the different effects that could affect or that could put some drawbacks on the optical fibers, like we have attenuations, we have distortions. So what is the effects that leads to decrease in the strength of light waves that propagates through an optical fibers. So the very first topic that we will discuss is about attenuation as well as the distortions. So these are the two basic effects that is responsible for deciding the maximum distance between the transmitters and the receivers. I mean, there must be a maximum distance between the transmitters and receivers, and if we require to amplify or if we require to regenerate our signals, if suppose that the strength, this distance between an transmitter and receivers is around 100 kilometers. So obviously we require some kind of devices like amplifiers, optical amplifiers, as well as the regenerators to regenerate our original signals. We know that if it is signal is traveling through a long distance, obviously there are several effects that going to that inculcate in the optical signals, which could affect the strength of that signals. So these are the two phenomena that decides that gives us the information about at what distance we should place an amplifier or we should place an regenerators, so that we can regenerate our original signals at a particular distance in order to properly receive our optical signals. So that is the overview about why we are studying this attenuation as well as the distortion. So now the question that arises by looking at the attenuation and distortions is about what are the loss or a signal attenuation mechanism in a fiber, and why and to what extent an optical signals get distorted as they propagate through the optical fibers. So we have already discussed in the previous slide that this attenuation as well as distortion is the main factor that would help us to decide what should be the distance at which an amplifier or a regenerator have to be placed between a transmitter and receiver, because we know that the optical amplifier as the optical regenerator are costly devices. So we should be very precise about the distance at which we should place these optical devices. So attenuation is basically a phenomena because of which a signal strength get attenuated, or there is a decrease in the strength of a signal at some distance from the transmitters. What are the various mechanisms related to attenuations, or what are the various mechanisms that are responsible for distortions? We will discuss in details in the coming slides. So now, attenuation, how we are going to calculate the attenuation, what is the formula that is responsible for getting the maximum, getting the value of that attenuation, so that we can predict the distance, safer distance at which we could place the optical amplifiers. So we are taking one example, like we are considering power launched at the transmitter, and suppose that we are considering the launching point of a power as origin, and we are considering some distance apart from that origin at which we are supposed to calculate the power, so that we could get the information at what is the rate at which your optical signal get attenuated. So what is the mechanism on which it is based on? I mean, it's going to follow a Gaussian distribution profile, or it will decay at a linear profile, or it decay exponentially. We will see in this formula. So we have considered a distance like Z as the origin at which a power is launched, and P0 is the maximum power that is launched, that is transmitted, or maximum power present in the signal that is transmitted from the transmitter. That is the P0, or we can say that P0 is the power at origin. P0 power at origin. That means at the transmitter side, and the power launched from a transmitter. So that is the power. Now, and we want to calculate the power at a distance, at some distance apart from the origin, and we are considering that distance as a L. That means origin is Z is equal to 0, and at some distance L apart from that origin, we want to calculate the power. So we will substitute Z is equal to L. Actually, this is PZ. So PZ equals to P0, that is the maximum power that was launched as the origin, and this power going to decay with various experiments and with the deep research by the researchers. They find that, they conclude that the power that is traveling through an optical fiber, they are going to decay exponentially if we are considering at some distance apart from the transmitter. So that is going to decay exponentially. So that's why we are having a factor that is e to the power minus alpha p, where alpha p is the attenuation coefficient or attenuation factor. So this alpha p is a attenuation coefficient or attenuation factor. Its unit generally expressed in per kilometer. So what is the attenuations that is inculcated inside the fiber per kilometer is something alpha. That is the attenuation factor or attenuation coefficient. Also, its unit can be expressed as Nepers per kilometer. So what is the formula for that? So we already know that Pz equals to P0 e to the power of minus alpha Pz. So if we are taking the natural, if we are taking the analog of that, then that will be expressed as alpha P, that means alpha P equals to Pz upon P0, right? So this is per kilometer. This is per kilometer. Expression for the attenuation factor along with 1 upon Z. So if you are considering at some distance L apart from the transmitter, you will substitute Z as L. So that's why it will become 1 upon L ln Pz upon P0. So that is the formula that is available to you for calculating the attenuation coefficient or attenuation factor in terms of per kilometer. So the more precise way of writing this expression is in terms of dB per kilometer, because we want to know what is the attenuation, in power in terms of a dB, and so that formula will be modified as dB per kilometer. So if you are taking dB per kilometer, so it will be a 10 log of your P0 upon P of L, that is maximum power strength and the attenuated power at a distance Z is equal to L. So that is this one, second one, that means this formula alpha dB per kilometer is the more precise way that any particular optical engineer going to use to calculate the strength of an optical signal at some distance, or what is the strength degradation in power per kilometer. So that is this formula is going to tell us. Now, so in terms of dBm also we can calculate the power. So we know that optical power is expressed in terms of dBm. For reference, we are going to use 1 milliwatt. That's why it is power is in dBm, right? So that because we always want to calculate what is the cost of our implementation of an optical link, and that cost also include what are the numbers of optical amplifiers that are required between the transmitters and receivers, as well as what are the number of regenerators that are required between the transmitters and receivers, because these equipments, these devices that is in between a transmitter and receivers, they cost a lot. It is not easy to develop a optical amplifier in the range of 1550. It's costly. So it also add on in the overall cost of the implementation of optical fibers. So this is the expression of power in terms of your dBm. So the power at some distance Z is equal to L can be expressed as P0, that means the power launched at the transmitter side, that is the maximum power of the signal, and minus of attenuation factor, that is alpha into L, so that it could become dBm, right? Because it is dB per kilometer and in terms of dB. So it will be dB per kilometer multiplied by the L, that will be kilometer. So we will get the power. So that is the power that is available at a distance Z equals to L. So one can use these formulas, that the previous one of alpha, to calculate the attenuation factor, and that include that attenuation factor in calculating the power at a distance Z is equal to L. So this is the optical fiber graph, that is the graph that is telling you the information about what is the attenuation that occurs at a particular wavelength or at a particular window of your optical system, optical fiber. So this is the graph telling us information about with variation in the optical window or with variation in the optical wavelength, what is the attenuations that get incorporated in the fiber in terms of dB per kilometer. This graph is giving us that information. So from this graph, one can easily conclude that we know that we are having a 3 optical windows, 850, 1300 as well as 1550 nanometer optical window. So in these 3 windows, we have to concentrate, we have to find what is the magnitude of attenuation in terms of dB per kilometers, so that we could use the optical fiber, or we could use only such wavelength that is responsible for getting a least attenuations. This graph is telling us that information. So in these 3 windows, this first window, second window and third window, these are the 3 windows we have already discussed in the unit 1. This 850 nanometer window, in this we can easily see that the loss of 850, it will be somewhere here, that the loss that is occurring in 850 nanometer is around 3 dB per kilometer. After that, if we are switching to a wavelength of second window, that is 1300 nanometer, in that case, the attenuation dB per kilometer get reduced to around 0.4 dB per kilometer. So we can easily see that. So this is the point telling us the attenuation at particular 1300 nanometer wavelength. So at 1300 nanometer wavelength, we can easily see that this is your 1300 nanometer wavelength, and from 1300 nanometer wavelength, we can conclude that the attenuation is around 0.4 dB per kilometer. So after this, the third window is 1550 nanometers. So in 1550 nanometer is what the wavelength that we are concentrating, because we want to transmit our information at a farther distance with a least amount of the attenuations. So that is the wavelength that are mostly used by optical engineers, because the amplifiers are also easily available at this wavelength. The repeaters are also easily available at this wavelength. So if you have the optical devices easily available at a particular wavelength, then you can use that particular wavelength. On the other case, although the 1300 nanometer wavelength gives you 0.4 dB per kilometer, whereas 1550 gives you 0.2 or 0.12 nanometer, 0.12 dB per kilometer attenuations. There is a little difference, a 0.2 difference between 1300 and 1550 nanometer wavelength. But the case here is in 1300 nanometer window that it is difficult at present. It is not easy to design the optical amplifiers or various other optical devices at this 1300 nanometer wavelength. So that's why we are concentrating on 1550 nanometer wavelength, in which we can easily find that the attenuation will be around 0.2 dB per kilometer, and the various researchers, with the modification in the techniques that they are using for purifying the fibers, they have reduced the attenuation from 0.2 dB to a 0.12 dB per kilometers. And there would be a very high possibilities that in the coming 5 years that could reduce down to even 0.9 or 0.09 dB per kilometer. So that is the information, that this graph is telling you the information at what wavelength you are going to transmit the signal inside the optical fibers. So this is the whole graph of optical of the attenuation versus a wavelength. Now we are going to discuss about what are the mechanisms that is responsible for attenuation in your optical fiber. So let us try to first. So we will discuss what are the mechanisms that is responsible for attenuation in optical fiber. We got the information what is attenuations, what is the formula with the help of which we can calculate the attenuations that is occurring inside the optical fiber. We have discussed that optical signal get attenuated in an exponential manner, and we have calculated the formula. We have find the formula for attenuation factor, and by including that attenuation factor, what is the power that is available at some distance apart from the launching power from the transmitter. So in this, the loss mechanism divided is responsible for attenuation is divided into two parts. First is your absorption, and the second one is the radiator, that means radiative loss. Now these are the two different loss mechanisms that is responsible for attenuation in optical fiber. Now these two different losses, we can easily get the meaning from their wordings. That means absorption loss. Absorption loss, if the optical power is completely absorbed due to some mechanism, that is your absorptions. And in the case of, that means in absorptions, power loss due to absorptions, the power get lost. That means you cannot recover back the power in any ways, right? So once it is lost, means it is completely lost, that because the power is completely absorbed by the material. Whereas in the case of radiative loss, the power going to be there. That means it's not like that, that the whatever the power loss that is occurring, you cannot recover back that loss. You can recover back that loss, but that power is totally useless, right? So that is the meaning of the absorption loss as well as the radiative loss. In absorption loss, power loss, whatever the power loss is occurring, that we cannot recover back that power. Whereas in radiative loss, we can recover that power. It's something like in the radiation loss, what is happening? We know that whenever the optical ray or optical wave is striking at the core and clad interface, and when it is strike at an angle which is greater than the critical angle, then a total internal reflection will take place. On the other hand, if we are maintaining the incident angle of the ray or wave, incident angle of the optical signal at the core clad interface to be less than the critical angle, then what will happen? The optical signal get refracted into the clad region. So some of the optical signals that is incidenting at an angle less than the critical angle, that will go into the clad regions. So we will say that the loss that is occurring in the signals because of the angle because value of angle less than the critical angle, so that loss is basically a radiative loss. Power get coupled inside the clad, and we can get that power, but the value of that strength will be very less, because that power that is traveling in the clad going to decay exponentially, and we are considering the distance of the width of the clad to such a value that whatever the power that is moving into the clad going to decay completely before it reaching to an end of the clad region. So absorption, in the absorption loss, if the power loss is occurring because of the absorption loss, because of the phenomena of absorptions, then there are two mechanisms. What are those mechanisms? First is your intrinsic and the second is extrinsic. Due to intrinsic phenomena, and second is due to extrinsic phenomena. Now what is happening in the case of intrinsic? We know that the optical fiber is made up of silica, that means silicon dioxides. In this case, what is happening? As your optical fiber is made up of silica, silicon dioxide. So in this case, a silicon, as silicon dioxide is a molecule, so in this case, a silicon atom is connected with a 2 oxygen atom with a covalent bond. Now, these atoms will be having some resonance frequency. So, if we are launching an optical signal at a frequency which is very close or which is even equal to this resonance frequency, then these atoms going to absorb the optical power, right? So, if we are considering this as this is a molecule, this SiO2 is a molecule. So there are two resonance frequency. First is your atomic resonance frequency and another one is your molecular resonance frequency. So we have to avoid both of these frequency in order to avoid the phenomena of absorption by the atoms or molecules of a materials from which a fiber is fabricated. So in this case, we have to avoid the atomic resonance as well as the molecular resonance. And we know that this one is absorbing power mostly, that means silica is having the resonance frequency in the infrared region. So if it is having a resonance frequency in the infrared regions, then we have to choose such a frequency, because we mostly operate that the optical signal, whatever the wavelength that we are launching, we mostly launch a wavelength in the range of infrared frequency or infrared wavelength range. And we also know that the silica going to absorb the frequencies in the infrared regions. So we have to be very careful at which wavelength we are going to transmit the optical signals, so that we can avoid the molecular resonance as well as the atomic resonance, in order to avoid the phenomena of absorptions. So in this, we have already discussed the power which is launched, power which is get lost because of the absorptions, we cannot recover back. So it is something with which we have to live, right? We cannot avoid this, because we know that the fiber is made up of silica, and silica is having a resonance frequency. And if we are launching an optical fiber at a resonance frequency, then what will happen? It's going to absorb that power. Basically, the overview is that it's not like that the power that is launched get absorbed. Means power have to move somewhere. That means the photon power is converted into a phonon power, right? Photon is converted to a phonon powers. As a result of that, the atoms will vibrate at their positions. So that in this way, the power get lost inside because of the intrinsic reasons. Another reason is the extrinsic. So this is the intrinsic reason, and another reason is your extrinsic reason. In extrinsic, very briefly we are telling, I am going to tell this so that we can consider it, we can continue from here in our next lecture series. So in extrinsic, because we know that there are various factors that is responsible for absorbing the power, like during the manufacturing process, there could be a possibility of absorption, or there could be a possibility of hydroxyl ion getting bonded with the silicon ion after replacing the oxygen atom. So in that case also, we have to avoid such kind of a thing. This basically occur because of the some problem get arise in the manufacturing process, and we know that in the atmosphere there will be a moisture. So we have to avoid of absorption of due to the hydroxyl ion that get covalently bonded with the silicon atom. So in our next lecture series, we will discuss from here. We will basically discuss some more points related to extrinsic factor, and apart from that, we will discuss also the power that get lost because of the radiations. So thank you all.